you guys hear me at the back? Is that okay? Yeah?
Yeah.
Okay, well, welcome to the Southern University Physics Nobel Lecture. As you can see, this year the Nobel Prize is awarded to James Peebles. We've got Michael Mayer and Didier Queloz for their discoveries in our understanding of the... You can read it, it's fine. Yeah, so I've got to make an announcement about the fire exits. There's two at the back and two at the front, and then the fire assembly point is outside the main doors opposite the car park. Yeah, since we've got two topics, we've got two speakers today. We've got Dr. Pasquale Barry and Matt Middleton, who are both researchers in their respective fields which relate to the prizes. We start with Pasquale.
Okay, so can you hear me first of all? Okay, I think the microphone is working. Okay, so I'm very happy to be here, and thank you for the invitation to give me this opportunity, because this Nobel Prize in Cosmology to James Peebles is the first Nobel Prize given in cosmology to a theorist, by the way. So there have been many Nobel Prizes given, 4 actually, so far 3, to cosmologists, but all for experimental discoveries, and we will see one example in particular. And well, I know that maybe there are school students. Is there anybody? No, actually, okay, because I was preparing some very basic slides, hoping to inspire them actually, but I don't think that in the end they came to me. But so for me, it is actually. Before, let me tell you very briefly how and why the Nobel Prize is assigned. So immediately after, okay, so I have to change directly here. So the way it works is that immediately after so Nobel in his will and testament said it should be assigned to the most important discovery or invention within the field of physics, I guess, in that year. And after the award of the Nobel Prize, immediately the committee of the Royal Swedish Academy of Science will invite some nominators, about 3,000, some of which are they are basically previous Nobel laureates, members of the Royal Swedish Academy of Science, so not the bulk. Then there are all professors of Scandinavian universities in physics, and then a selected number of professors from hundreds of universities around the world. Then there will be a kind of short list at the end of January for 2020, and then the committee will assign the final winner. Notice that the prize is rewarded for a particular, especially important scientific discovery, and it's not a career Nobel Prize. So if you wrote only one very, very good paper for a big discovery, is better than 1,000 papers, let's say, in a certain sense. So it's really it's not a career prize. I was curious, and the youngest Nobel Prize in physics was William Bragg for diffraction experiment in 1915, and he was only 25. Probably it was a different time. Then Einstein was 42, he was a bit older. Dirac and Heisenberg were 32, Fermi 37. So there were many, let's say, young winners. Probably Peebles is more on the older side, so it took some time. And the title that was proposed is Understanding the Universe. And I added a small appendix by listening to its music. And Matt, by the way, we'll talk in the second half about a simulation for the discovery of the exoplanet, was asking me why music, so it's, you will see why. But I will show you that indeed, in order to understand the universe, it's very similar to understand how a musical instrument, an acoustic box more particularly, works. So there are many physical analogies from that point of view. And indeed, I will do some references to very simple things, so a guitar, music, oven. So it's true that we will see the universe works as an oven. And also to sports, because that reminds me the time when I was inspired by a great cosmologist, and that marked the beginning actually of my interest in cosmology. And let's say that the discovery of the cosmic microwave background represents in science, in physics, in a certain sense, the same that the discovery of the Rosetta Stone represented to decrypt Egyptian hieroglyphs. And it's really gave us the way to decrypt the properties of the universe, how the universe works and evolved, and the history of the universe. So these are, as we will see, the CND temperature anisotropies measured by the Planck satellite. So it's a picture that quite relatively recent, in 2013, and it really contains a huge amount of information, as we will see. So this was really a slide for school students, but okay, I understand there are not. But for me at least, I remember that I listened about the discovery of the CMB by a great book written by Steven Weinberg, who is one of the builders of the standard model in particle physics. And I remember at the time, actually, I was more interested in sports, in particular in running. But then I got injured, and so I was, that winter I could not do much sport. So I remember that I bought this book, and, and it was my last year at school. So I was really excited, and it really inspired me. And in a certain sense, it marked my following future life, because I'm still now devoting my academic research to cosmology and particle cosmology. And actually, I suggest you to read it, because there was also a revised edition that is more recent with the most recent updates. And in this book, Weinberg tells very nicely the story of the discovery of the CMB. And it tells the story of these two radio astronomers from the Bell laboratories that were, after having tested basically this new horn antenna for radio communication with a satellite that was called ECO, they were also astrophysicists. And so they decided, since they could detect a new range of frequencies, whether at those frequencies, never explored before, the galaxies was emitting radiation and what kind of radiation. So they wanted really to study the radio emission from the galaxy. The antenna could basically follow an object in the sky. It was supposed to track basically this satellite. And so therefore it was easy to rotating this antenna to remove astrophysical sources, in order to understand, first of all, if there was a kind of a noise in the antenna. And indeed there was, and they were able, with some techniques, to remove the electric noise from the antenna itself. But still, after that, there was still some noise. And at that point, they thought, they really didn't know what could be. They thought maybe the atmosphere could not be the atmosphere, because also there will be a modulation when you rotate the antenna. So they thought that maybe the antenna was hosting some pigeons, so they started to shoot with the rubber bullets. I was reading in the book. The pigeons, and then they cleaned the antenna from their droplets. Still, they still had this noise that was constant across all the sky, and so it was irreducible, so they could not get rid of it. At that point, they called a colleague of them at MIT, a radio astronomer, that told them, look, actually, I know from a colleague at MIT that there was a seminar by young physicists on early universe, and how within that new theory, at that time it was still a hypothesis, that was dubbed Big Bang theory, and we will see why and who gave this name. There could be some relic radiation, and maybe this is what you are detecting. And so in the same 78, so 13 years after, let's say from shooting pigeon, they got the Nobel Prize for this discovery. That, in my opinion, probably is perhaps the greatest serendipitous scientific discovery ever, because they were looking for something else, but certainly they were good in understanding that they discovered something very important. Indeed, in 41, there was another anomalous signal, astrophysical signal, that then after we understand it was already a detection of the CMB, but at that time the experimentalists thought it was just simply something wrong in their experiment. So that was very interesting. And the point is now to understand the cosmological interpretation. So the Penzias called, therefore, this scientist, that was Jim Peebles, who gave the seminar at MIT, and he was working with a more senior professor, Robert Dicke, who was the leader of a group, and they were, Peebles was the theorist, they were trying to test a prediction that was done already in 1948 by, we will see, Alpha and Hermann, about the existence of this relic radiation. And in particular, they wanted actually to test with an experiment. So they were just starting to do their measurements on the top of the roof of Princeton, when they received this call from Penzias, and basically, well, they were scooped in a certain sense. Indeed, only 1 year later, they were able to confirm the measurement on another frequency, by the way. However, they decided, because obviously they had the cosmological interpretation of the discovery, Penzias and Wilson, if you read the paper, they only mention this possibility, but they very, in a very dry way, they quote just this observation, a measurement of excess antenna temperature at 4,080 megacycle per second, so 4 gigahertz. And they both were thanking each other in a certain sense, but obviously, today what is important is to understand the cosmological interpretation and why this signal is so important in cosmology, and I would say in all modern science. So the model that Dicke and Peebles and collaborators were studying was based on general relativity of Einstein, and in the general relativity of Einstein, gravity is described in a geometrical way, and if you apply to cosmology, and like Friedman, you make an assumption that the universe on large scale is homogeneous and isotropic. Fortunately, things are not that complicated, because you can have only 3 possibilities, and they are the same possibility that you have thinking of a bidimensional analogy, where the curvature is constant, or a d-dimensional surface, and embedded in a 3-dimensional space. If you think of 3-dimensional space embedded in 4 dimensions, still you have only 3 possibilities. So you either have a closed geometry, so in that case it would be the surface of the sphere will become a hypersphere, either an open geometry, an hyperboloid, or a flat plane. So we will live in a hyperplane in that case. And you see that these 3 possibilities are identified by a curvature parameter. So curvature for a closed geometry is positive, negative for an open geometry, and vanishes for a flat geometry. In this particular case, then you have only one parameter describing your geometry, that is basically the radius of curvature, and if you normalize at the present time, then you can introduce the scale factor that will be 1 at the present time, and then how the radius of curvature, think of the sphere, changes is described by the famous Friedman equations. That in the end, it's quite complicated, but mathematically it's just telling you that the sum of a kind of kinetic energy associated to this motion plus a potential energy is constant. And that makes simple to understand, much simpler to understand the solution of these equations, because you can introduce an energy density parameter where you substantially compare the energy density of the universe to a critical energy density that will be the energy density in the flat case. And you have now a correspondence between geometry and the amount of energy density. This is typical of general relativity, because the geometry is substantially determined by the distribution of energy. And so in this special case, the energy density will determine whether your universe is closed, open, or flat, depending whether the energy density is greater or equal or lower than the critical energy density. Defined in that way, substantially it depends on what is the velocity given by the Hubble constant of this function today. The Hubble constant is the derivative of the scale factor at the present time. And then you have a simple picture. If you consider just matter, so the energy is just in mass density, then the potential is negative, and the system evolves like a ball on the cliff of the hill given by the potential. So if you start from an initial value of the scale factor, if you give enough kinetic energy, the ball will either come back, or if it's enough initial energy, it will always, the universe will expand forever, and so the analogy is that your ball will continue its motion at infinity. In this, however, Einstein introduced a twist. Einstein was not satisfied by this dynamical model. At the time, in 1917, he gave the first cosmological model, and there was no evidence of the expansion of the universe. So he thought that the universe, like most of the people, the universe was static. So he was not at all satisfied. And what he did, he introduced in the equations the so-called cosmological constant that could produce a repulsion gravity. While matter always is attractive, so this ball will always slow down, the cosmological constant can provide a repulsion, and so the potential shape changes. Now, if the ball reaches the peak of this hill, then it will start an accelerated expansion. And basically, notice that the cosmological constant is associated to energy density of vacuum. So actually, that's why there is a point when it dominates. During the expansion, the energy density of matter is diluted, so galaxies will be pulled apart and the mass density decreases. In the case of the cosmological constant, this corresponds to energy density of volume. If the volume is generated by the expansion, the energy increases. That's why it dominates at some point. Lemaitre while Einstein, after the discovery of the expansion of the universe, was upset with himself, the greatest, he called this the greatest blunders of his life, but his mistake was to think that the universe was static, because the static universe will correspond to place this ball on the top of the hill, and clearly it's unstable. So it's not a real, very good solution. Georges Lemaitre was actually a great fan of the cosmological constant, and he continued to study cosmological dynamical models with the cosmological models, and he made a radical assumption. He said, what if the initial beginning of the universe is with a scale factor that is much less than 1, so really we would have a universe, our observable universe could be thought, one can think that our observable universe can be compressed in a big atomic nucleus that he was calling the primeval atom. Why he was thinking of that? Because he, at that time, they didn't understand what was the initial kick of the expansion. So why there was this initial energy. At that time, there were studies in radioactivity, and he could think that the decay of these nuclei was actually providing the initial energy for the expansion. He was not calling this theory Big Bang, but Fred Hoyle in 1949 at BBC actually was a supporter of a opponent theory, the steady state evolutionary universe. And he was saying that basically, in these theories, the matter is created in one Big Bang at a particular time. He was quite sarcastic and ironic. Jim Peebles, in an interview a few days ago, he said that actually the word Big Bang is misleading because it makes you thinking of a big explosion, while it's not like that. There is not a point, privileged point in the universe. Actually, we have seen it. The universe is homogeneous and isotropic, and that means exactly that there is no privileged point, so it's inappropriate. But he said, now it's so established that even though I dislike it, I've given up, and I still use myself Big Bang. It became even a famous TV sitcom, the name of a famous sitcom, so it's really impossible to get rid of this name. Peebles had a role in going from mathematical speculations, from just equation to physics, particle physics and nuclear physics. And first of all, these people, Gamow and collaborators, they thought of the possibility of explaining the nuclear abundances in the universe through this Big Bang theory. So what they were understanding is that if you go back in time, the density is higher, but also the energy of the particle is higher, and you will reach energies where nucleus cannot exist, but actually all nucleons, protons and neutrons will be decoupled. If you start from this state and you let the universe evolving, then by aggregation you will form the other nuclei. And what they discovered is that in order to understand why the universe in the end, primordial, is made only of hydrogen and helium, all the other 80 elements we observe are produced mainly in stars, basically. And by the way, with the discovery of the neutron merger through gravitational waves, and through gamma observation, we could see really how gold is produced in these very violent astrophysical processes. So much later, so even though these element are produced after, the universe, in the universe what we observe is mainly hydrogen and 25% helium, and they could understand that only if together with matter there is also radiation. Why? Because otherwise, the radiation will stop the formation of 80 elements by photodissociation, in particular with the split the deuterium. And when the deuterium finally forms and then you can form helium, it's too late. Somehow these nuclear reactions stop, and you are left only with hydrogen and helium. All the deuterium will be reprocessed in helium form. Actually, there must be a lot of radiation. In the latest calculation, we know that there must be, for each baryon, for each nucleon, there must be basically 1 billion of photons. So a huge amount of radiation, and that's why after, 1 year later, this work together with Gamow, Alpher was a student of Gamow, and together with Hermann, they finally arrived to the conclusion that there could be a radiation at the present time of about 5 Kelvin degrees. While what we observe now is 2.7. So they were very close, even though there were big uncertainties, so they were a little bit lucky. But somehow they didn't push this prediction, and this prediction was forgotten for a long time, until Penzias and Wilson did their measurement. But today we know that it was a correct picture, because what happens is that, moreover, is that these photons will scatter, also will destroy atoms, so that electrons and protons are fully ionized, if you go back in time. And also photons will establish a thermal equilibrium, and only after the universe expanded enough that atoms can recombine, photons can travel in a straight line to us. And this is so this fossil radiation is what Penzias and Wilson detected. And today, this decoupling happened at temperature of 0.3 electron volt when atoms recombine. It's a temperature, notice, that corresponds to energies much below the atomic binding energies, because simply there are so many photons that even if you go in the tail of the distribution, there are still many photons with an energy of 10 electron volts, the typical atomic binding energy, to destroy atoms. So you have to wait that the temperature drops down at 0.3. The temperature in a thermal environment drops like the inverse of the scale factor. So now, what is the spectrum of the CMB? If you have a black body, you predict a Planckian spectrum. But in nature, actually, it's not easy to find the perfect Planckian spectrum. A micro-oven has something that resembles a Planckian spectrum, but is very different. That, by the way, works at the same frequencies of the CMB, so the gigahertz. And this is the solar spectrum is a little bit better, but if you now consider the CMB spectrum, it's by far the most perfect Planckian spectrum in nature. And in this case, so in the case of black body, what you know is that thermal equilibrium is established because photons are emitted and absorbed many times by the walls. Here you don't have walls, but you have basically these photons scatters many times with the electrons. So there are no walls, but there are scatterings that redistribute momentum and energy in a way that the thermal equilibrium is reached and you observe a Planckian spectrum. People also recognized that not only there should have been a uniform temperature, but because of the motion of the Earth through the universe, there should have been a portion of the universe a bit colder than the other ones. And indeed, this dipole anisotropy was detected. This is the people's formula, and today that tells us that the Earth is moving with respect to the so-called co-moving frame with a velocity of about 370 kilometers per second, a motion due to the combination of annual motion of the Earth, motion of the solar system in the galaxy, and so on. In addition to the dipole anisotropy, there are primary anisotropies, and the Planck satellite is the one that measure this primary anisotropy when you subtract the dipole anisotropies with greater resolution. They were first detected by Cody, and Smoot and Matter got the Nobel Prize for this discovery. What is interesting, and it was noticed by Sakharov, is that if you have that, this shows that in the universe there were initial perturbations, so it was not perfectly homogeneous and isotropic. And actually, that is good, because otherwise we could not explain how galaxies form. Indeed, Sakharov understood that also that during the period when radiation and the electrons and matter are coupled together, matter undergoes some acoustic oscillations. So if there is a perturbation generated by some primordial mechanism that today we think it's inflation, and this perturbation well is in the form mainly of cold dark matter, and the concept of cold dark matter was another basic concept of cosmology today introduced by Peebles. This perturbation will undergo some oscillations under the gravitational force and the radiation pressure. And these oscillations will get imprinted in the CMB, and they are basically these spots that we observe. Substantially, hotter spots are those with a low density, and cold spots are those with a high density. So a point that is on the bottom of the potential well, in order to climb the potential well, will lose energy, and so it will become colder. And what is important is that if you do a Fourier analysis, a sound spectrum, you will observe acoustic peaks. Where these acoustic peaks come from, and they are basically the prediction by Peebles that I think deserve the Nobel Prize to him, I think. This is why, the main reason why he got the Nobel Prize. It resembles very closely what now we measure with the Planck satellite. So the theory made in 1970 was correct, and these peaks contains a huge information on all the cosmological parameters. Very similarly to how, from the sound spectrum, physics in the acoustic department, they understand how a violin, for example, is made of, or how you can change the sound spectrum of a violin, even changing the chemical composition. So all cosmological parameters influence these peaks, and for example, in particular, what you have is that the first peak will tell you about the geometry. You could ask me, but where is the acoustic box in the universe? It's infinite. The acoustic box is given by the fact that light and sound in particular cannot travel faster than the sound speed, that is approximately 1/3 of the light speed at the time, and as a finite time. There is a beginning of time with the singularity, the Big Bang. So the maximum distance traveled by sound is your acoustic box. And the position of the first peak is basically given by the angular size of the sound, the so-called sound horizon in the sky. And this is given simply by the size of the sound horizon in the co-moving scales divided by the distance to the CMB. So it's a simple calculation. But if the universe is curved, the angular size can change with the geometry. So you see there in this picture the difference when the universe is closed. The sound horizon will look smaller, and then the angular size will be smaller, and the multiple moment will move to the right. So the position of the first peak tells us actually that the universe is very close to be flat, and the second peak, or more generally the even peak tells you about the barium content, and the third peak tells you that there is a lot of cold dark matter. So in the end, and this is my conclusive slide, sorry for the delay, really, this is the picture I like, is that we have a kind of a pizza, cosmic pizza coming out from this, where the universe is made of barium only for 5%, cold dark matter 25%, and most of the energy of the universe is in the form of this cosmological constant that Einstein rejected and that was reintroduced by Lemaitre. It was after forgotten, and Peebles was the one at the beginning of the 80s proposed both cold dark matter as a dark matter and reintroduced lambda in the cosmological law. So certainly can be considered one of the fathers of the lambda CDM model. However, not everything has been understood, because what is exactly the nature of dark energy, of dark matter, is unknown. In particular, in the standard model of particle physics, we have no explanation. We still don't know what is the cold dark matter, so there is still a lot of work to be done to reconcile the two standard models, the standard model of cosmology and the standard model of particle physics in a unified picture. So I hope I inspired, so that's why I hope I inspire young people like you, because there is still a lot of work to do in particle cosmology. And thank you, and sorry to Matt for being late. Maybe you can ask questions at the end. No, it's or maybe you can prepare, you can set up your laptop. Yeah, okay. If you have any question while Matt is any kind of question. I mean, also don't worry how you think it's crazy, or don't worry at all.
How did they know that the third peak on the diagram was to do with dark matter?
Okay, that I was a bit fast. So basically, you have this compression, and the more you have that, basically, the first peak corresponds to those regions that have been able to do only one compression. And that determines the geometry. Those that are able to bounce once are basically the odd even peaks. And that tells you how much baryonic matter was there. The more baryonic matter there is, the more deeper is the compression. There is more gravity, basically. The third peak are those oscillations where you have three, basically, you have one compression, decompression, and compression again. And it works fast enough only if there is a lot of dark matter that doesn't move and makes the potential well very deep. So it makes everything faster. So that's why the third peak and also the following ones are indicators. The fact that it's so pronounced tells us that there is a lot of cold dark matter. So it's based really on how fast these oscillations happen in the universe. Okay, I leave the word now to what happened in the universe late and the possibility that might be live.
Okay. All right, guys, can you hear me around the back? Yeah? If not, just I don't know, wave at me or something, we'll see what happens. Okay, so immediately a disclaimer. Pasquale, wherever he's sitting now, is a cosmologist, and he got to talk about cosmology. I work on black holes and neutron stars, so I get exoplanets. Right, so that is fair. Okay? So immediate disclaimer that all of the questions you ask me will be answered in an extremely disappointing fashion. Okay? But that's why God gave us Wikipedia. So, I get to talk about exoplanets, and the other half of the Nobel Prize. Jim Peebles got half, the exoplanet people got a quarter each. So, this is a very low level, okay? Most of the guys who I recognize from my class will already know this stuff. Yeah, woo! Right, okay. For those of you who don't know, right, this is for you guys mostly, okay? So you can probably chill out and learn some interesting things or look at pretty pictures. So let's start with the title, The Discovery of an Exoplanet. Exo means outside of. So really what this is about are planets outside of our solar system. We're all familiar with the 8 planets in our solar system, although I see some people in the audience who will be with me and believe there should be 9. Pluto, right? Yes, yes, bring it back, okay? Unfortunately, we live in that world. So why? Why do we care about planets and other solar systems? There's a profound reason, and then there's more of a scientific reason. The profound reason is that we want to understand, as a human race, whether or not we are alone in the universe. There's a very famous experiment called SETI, the Search for Extraterrestrial Intelligence, and they are scanning the sky, looking at nearby stars, and they're looking with their radio receivers, trying to find alien life. And that's a hugely admirable goal, because we want to know if we are alone in the universe. Now, it will help enormously if we can find planets where we think there might be life, because then that cuts down the problem. There's a few 100 billion stars in the galaxy, and we'd like to make life just a little bit easier for ourselves. So that's the profound reason. Perhaps a more scientific reason is that we want to understand our own solar system. When we look at the planets, we have an idea of how they might have formed. For those of you in my class, you're fully aware that you start with a particle of gas that collapses down, it rotates, and then planets form out of that. It probably looks a little bit like this. And that's fine, but we have a sample size of 1. And for those of you doing stats, that doesn't give you great errors. Okay? So what we want to do is look at other solar systems. Do they have 8 planets? Do they have planets that all orbit in the same or very similar plane to each other as we do in our solar system? Do we have strange behaviors? Do we have binary stars, etc., etc.? Do we have something on very large scales like the Oort cloud, which is where our cometary nuclei live and give us a long period comets? We can't understand that until we find these other planetary systems. So that's the other reason why we want to look. But there's a problem. You might think, well, why not go out? I've got a fairly powerful telescope. Why don't I just go and look? I can see Jupiter through my telescope. I can see the Galilean moons. I can do all these wonderful astrometry just using my eyes. So why don't I do that? Well, here are some of our local stars, some fairly important, famous ones. Proxima will appear later on. Here's the Sun. And this is a size scale of about 15 light years. For those of you who don't work in astrophysics, a light year corresponds to around 6 trillion miles. That's pretty big sort of scales that we're talking about here, pretty enormous. And these are the stars that are nearby. And the problem is that if we take our nearest ones, this is Proxima Centauri. It's only about 4.2 light years away, so merely 24 trillion miles away. Now, actually, it's not actually impossible that we could resolve a planet going around that star. If you have a separation between that star and a planet, say it's similar to the Earth, called 1 astronomical unit, in principle, we could resolve that. We could separate those two out. That's not actually an impossible challenge. The problem is that the reflected light from the star, which is how we see it because they don't emit their own light, is incredibly weak. And in fact, the glare from this star completely dominates it. So looking directly like that is very, very difficult. We don't like doing difficult things because it's hard. It costs money. We don't want to do that. So we want to do something else. And there's a couple of ways we go about finding these planets in the solar system. There's more than 2 techniques, but I'm going to focus on the 2 that have been the most successful. The first one is that we simply look for a planet crossing in front of the bright disk of that star. There was a transit of Mercury only, a couple of weeks ago? Something like that. Did anybody get to see it? Yeah? Yeah? Cool. Excellent. So it's a fairly similar proposition. So what we do is we look for the drop in light that occurs as a planet transits across the face of the star. So here we have a fairly Earth-like planet going across, and we can see this nice broad dip. We might have a Jupiter-sized planet, and that presents a very large dip. So if we go out and look at lots of stars, we can hope to find these dips that tell us that there is an object there that is crossing the face of the star. Now, immediately, you probably recognize there's an issue. And that issue is this only works if we're edge on, if those planets are going around in a way that we can see them. If this was oriented so the planet was going around like this, we'd never see that. We'd have no way of finding that. Now, the second way, this sort of normally brings a bit of dread to people's souls, these 2 words put together. Okay, where are my helpers? Come on, I'm an absolute bastard. So I get my first year undergraduates to come and perform for me. Come here, dancing people, come on, right. So the second idea is nice and simple, right? So come here, you are the star. Yeah. Right, okay? You've been told that too many times in your life. So this is my planet. Okay, it's very low mass. Right, there you go. So you can imagine, I'll do that, spin around. I'll tell you when to stop. If there's any friends of his in the audience, please take a video of this. This will haunt him for the rest of his life. You can see that, you take the video, excellent. You go, haven't tell you stop. Right. You can see that he's basically the axis of rotation. Okay, you can stop now, you've done very well. Okay, now hold each other. Yeah, totally, okay, well, okay, now spin around. There you go. There you go. Now you can see that then we're not spinning around on his axis. The axis is between their hands. Okay, now stop because we didn't get sign off from health and safety. Okay, let's just hang those guys. Right, great. But what you saw there was the movements of the centre of mass. Because when there were a more similar mass, the centre of mass got pushed out. It was in the middle of their hands, basically. Now you can imagine that that is the situation if I've got a low mass planet, or if I've got a much bigger planet. We see a bigger change. Okay, so what would that actually look like in practice? Well, we'd have a star and a planet going around, and you can imagine they're orbiting around, they're holding hands, and they're orbiting around a common centre of mass here. So what we actually try and detect on Earth using our instruments is the change in light that's coming from this star. Now we don't do that directly from its light. I will go back and show you that again. We use, is it going to do it? No, don't do that yet. Go on. What we look for are the shift in atomic lines. So you can see there's atomic lines here. They're moving as a consequence of the star going around. It shifted in one direction, and then it shifted in the other. So what we do, and this is a real thrill for me because I never get to use chalk. It's great being an academic. Wow! Right? We do lambda observed minus lambda in the lab over lambda in the lab. So that's just the wavelength of a given atomic line. And that's approximately equal to the velocity over c. So what we would see over time as that planet was going around, we'd have velocity here. We normally use something like kilometers per second. And we see it as a sinusoid, because it's orbiting around a common centre of mass. Now, weirdly enough, this technique was first applied to find exoplanets not around a normal star at all, but around a dead star. This is a pulsar. So this is a neutron star. There's a massive star that went through its life and then collapsed down and left this weird atomic degenerate core. And radiation spills out to the poles and sweeps across us. And it does so with a regularity. What is that? It does so with a regularity which is better than atomic clocks. So much like the atomic lines which we're moving, we can look and see when that beat period is moving. And people did this back in 1992, and they found not just one planet, but multiple planets around a pulsar which has a designation you don't care about, but if you do, it's PSR 1257 plus 12. The neutron star was spinning around 161 times per second, and that was really the first detection of an exoplanet. Okay, but it kind of sucks because nothing's going to live on those planets. Pulsars emit huge amounts of high-energy radiation. High-energy radiation doesn't actually turn you into the Hulk. The comic between lying to you, it just kills you. So there's probably not a lot of life on those planets. So what we really want to look for are planets around other stars, which aren't dead and aren't going to kill us. And this is when we get to sort of the centerpiece of this result. So here we have 51 Peg. It's in the constellation of Pegasus. It is a sun-like star, and it is 50 light years away. So it is a long way away. Now these chaps, and I'm going to also totally mangle his name, Didier Queloz, maybe, is that his name, and Michael Meyer, looked at a whole bunch of stars. And they did so not with this, but they did so with this, the Haute-Provence Observatory. It is a 1.93 meter telescope. And what they were looking for were these shifts in the atomic lines, which told us that there was a planet present. Now, what you can actually do with a bit of physics, which I'm not going to take you through, but you can use this period, so peak to peak or trough to trough, call that T, and this height, which we confusingly call K, you can put them together and you can actually obtain the mass of the exoplanet. So those are fairly simple, straightforward ingredients. There is a missing ingredient I'm going to tell you about. So what? Right? Okay? So that's what they were looking for. They wanted to find these shapes. Now, in 1994, when they started looking, they didn't have fantastic sensitivity. So they did the best they could. They actually had a sensitivity around 15 kilometers per second. These days, we get to about 1 kilometer per second. So we do a lot better now. But that's what they had to deal with, and they looked at a load of stars. And this is what they found when they looked at 51 Pegasus. And this is, if you haven't noticed, what I've drawn on the board. In this case, in meters per second. Don't worry about this thing. I'm just telling you about how we folded it on the period. What did they do? They got a period, 4.2 days, and they measured this amplitude here. And from those values, they determined that there was a companion to this star, which had a mass of somewhere between 0.5 and 1.2 times the mass of Jupiter, and a distance from its star of 0.05 astronomical units. So it's 5% of the distance between the Earth and the Sun. That's incredibly close. And this was not only the first exoplanet found around a Sun-like star, which is thumbs up for finding things that are still alive, but also the very first example of using this methodology to something that isn't full sun. So this was a huge result. And as a consequence of that, people then started thinking, maybe we should do this more. So they had a paper in Nature, which for those of you who go into academia would be something that is either a gift or a curse. And this came out in November 1995, and obviously, enormous deal. For your interest, the planet was originally named Bellerophon. Yeah, actually, I've never actually said out loud, so I didn't actually realise I recognised the word Bellerophon. But then the IOU, in their wisdom, changed it because they suck. And it's now called Dimidium. Dimidium comes from the Latin, meaning half. And because the mass of the planet is more than or equal to half Jupiter mass, it kind of fits. So, okay, so that's kind of the picture, that's what they found. Okay, but, so what? Okay, one is the first exoplanet around a Sun-like star, that's quite a big deal, and the first example of using this radial velocity method, this thing here. But one thing we've immediately established is that that solar system doesn't look like ours. Jupiter, our big Jupiter, sits at about 5 astronomical units, so 5 times the distance from the Earth to the Sun. This object sits at 0.05 astronomical units. For context, Mercury is 0.4. So this is extremely close to the star. And we have to then explain, how can it be there? We don't think we can make planets that size, that close. In order to make planets that big, we have to make a whole load of ice. We have to get it together, and then we create our envelope, and then we can make something as big as Jupiter or Saturn. You can't form them that close. So how did we get there? Well, the answer goes back to that picture I showed you about how we think the solar system formed. We think that if there is one of these disks, that something like Jupiter can interact with it and slowly migrate inwards. We also think, for those of you who are interested, that Jupiter, our Jupiter, did also migrate inwards from out here somewhere. So it's not just in this weird case, but it's also in our solar system as well. So it's an example of an exoplanet. It's also the first example of an exoplanet that close and that big to a star, and we refer to it as a hot Jupiter. It's hot because it's hot, really hot, over 1,000 Kelvin, very close to its star. It's also what we call a roaster planet. So it has completely forced us to rethink our ideas of solar system formation. So going back to that original idea of why we're doing this in the first place, that's a big tick mark. Okay, so that's probably what it looks like. Right. And there are other questions about this planet. For instance, can it hold on to its atmosphere? If it's that hot, it must be very close to the point where it's going to lose all of its gas. We call it Jeans retention. So maybe the mass is wrong. Maybe this is slightly more massive and has enough gravitational potential energy to hold on to it. So it's still a very interesting object. Okay, so what's happened since then? Because that was 1995. Let's skip forward a bit. People started paying attention. People woke up to exoplanets. They thought, wow, this is now a feasible thing. Then all this time got assigned to doing velocity, doing this, making sine curves. And then the number of exoplanets started to rise and rise and rise and rise and rise. Then it got a huge boost with the launch of this thing. This is Kepler. And it's a transit finding mission. It only lasted, I think, about 3 years. And this is what it's looking for again. Remember, it's looking for these dips. And it has been extremely successful. To give you an idea, this is what we call the Kepler orrery. And if anybody is motion sick, you might want to look away. Oh, that's pretty difficult to look at. And this gives you an idea of some of the systems that are the Kepler. I don't want to look at it. It makes me feel a bit rough. Okay. So to give you a historical perspective, then, this is kind of what it looks like from now up until about 2018. So yes, okay, there was something big formed there, but forget about that. This was our pulsar. Then after wait 3 years, then we discovered 51 peg in 95. And look, the numbers are going up. This is through radial velocity measurements, so this thing down here, up they go. Now they found transits. Don't worry about that. Up it goes, up it goes. Now Kepler was launched. Now let's see what happens to the green. And boom. Fairly substantial improvement. So the radial velocity things have been fairly steady, but you can see that the way finding exoplanets with transits have been kind of profound. So we now know of thousands of exoplanets. And the idea now has kind of shifted. The focus is shifted not, yes, we want to find more of these things. Yes, we want to find more Earth-like planets especially, but we also care about where they are. So it's not enough to find a planet. Because, for instance, 51 peg B, Dividium, that's right next to a star. You don't want to live on that. Right? That's bad. You want to live in a nice place with water. You want to find something in the habitable zone. So this is the zone in which you're not too close to the star that you're not going to have any water. You're not too far away that it's going to freeze. So unsurprisingly, we live in our habitable zone. And we want to find out where these things are. And again, we can use something similar to this. So this information encodes the mass. It also encodes the distance from the host star. So we are now very interested in finding not just planets, not just exoplanets, but exoplanets which might harbour life. And that's going back to that first more profound question. So in total, to date, there are 17 known planets that live in the habitable zone. Only one of those is less than 10 light years away. And it's actually, weirdly enough, our nearest neighbour star, so Proxima. Proxima is actually in a triple system of Alpha Centauri. It's very close. It's, as we saw before, 4.2 light years away. So it's basically on our doorstep, essentially. If we can ever figure out how to get there, the speed of light will only take us 4 years. Great. Okay, I believe in this. Right. And some of you might have seen this result. It was a major result about 2 years ago, where people said, oh, this is not as pretty by any stretch of the imagination as a result of 51 peg, but this line here told us that there was an exoplanet around Proxima Centauri, and it probably looks a little bit like this. It's Earth-like, and it sits in its habitable zone. That's awesome. Why does it look like crap? Well, it turns out that Proxima, unfortunately, is a dwarf star, and dwarf stars are incredibly magnetically active. That means there's a lot of high-energy radiation, a lot of nasty stuff going on, and it's probably stripped the atmosphere of the planet. So it's nice, you probably don't want to live there. But that sort of result has only come about because people invested the time and the money in doing these studies. And that only happened because of Didier Queloz and Michael Mayer. So that is why they got the Nobel Prize. And I'll leave those guys up there, and I'll finish. Thank you very much. And I dread to ask, are there any questions? Sorry, it looks like I'm quite threatening. Yeah?
So if exoplanet is really small, does that make it harder to intercept?
Absolutely, yeah. So as you kind of saw with this, the position in the centre of mass and that radial velocity wobble means that it's very small. So the amplitude of the sine wave is very low. Plus, if you're looking for transits, the drop, that trough is related to the areas. So, of course, with a small planet, we've got a problem. We have found some small planets there, smaller than the mass of the Earth.
Do we know the limit of planets we can detect?
I'm sure someone does. In terms of radial velocity, it's around 1 meter per second. So it means an order of magnitude better than they were able to do, which is, again, almost certainly a consequence of just increasing the technology to meet the demand. In terms of transits, that depends very, very much on cadence, so how often do you look? Because you might look away and, oh, it's happened whilst you were looking the other way, right? So Jupiter has a very long orbital period and you have to wait a long time to find it. And the other thing is purely sensitivity. You have to be fairly sensitive to find some of these things, especially with lower mass planets. Yeah.
Just about the Nobel Prize in general, is it true that Alfred Nobel came up with it because he did want to be remembered just for dynamite?
I don't know, but let's go with that, yeah. That makes it sound like that's a delusion.
No, what happened is it's quite fun. A few years before his brother died, he was really rich. He was like and someone thought that he was journalist and he wrote an obituary that said, finally, the man of the left died. And he was still alive. He was his brother. So he had this, and he was very touched. And he said, well, I want to be remembered for something else. And he devoted the equivalent of 350 millions of pounds.
The moral of the story is fake her own death and see what happens. Anything else?
That's about the first sign. There was a little dip along all the peaks.
There's a dip on some. You mean this?
Oh, no, the first one.
The very first one. You don't mean that, do you? Oh, don't worry about that. That's just scatter. something statistics. That's a good question. I mean, you could also argue that there's some instrumental dropouts now. I don't know if there could be a systematic issue. I can't actually remember whether there's additional. If there were an additional system, you'd see an extra phase effect on it, so it's almost certainly not that. It could be that the actual star itself is variable, because stars do change their emission. Certainly if they're fairly active, you can see fairly large changes in their optical night time. It could be that. I don't know enough about the star, but it's the solar mass main sequence star, which leads me to believe probably not. So, but we won't call that today.
Okay, thanks everyone for coming. I want to say a huge thank you to Tom and Noe, our outreach team, for setting this all up. Yeah, thanks for coming. See you next year.